Hey everyone, and welcome back. Today we're going to be proving the following statement. Uh, as a reminder, I like to start by breaking down the statement. So here we have the for all m greater than 0, there exists an n greater than 0 such that 2n plus 3n is less than m times 4n. I guess I can highlight that too. No reason why not. All right, so this was a problem that we have previously solved in our own classroom, but we are going to create a video of it as well now. So a reminder, what we're trying to do is we are going to be trying to pick an n such that this is true for all values of m. So to start off with our rough drafts, with our rough work, we're going to just observe that 2n is strictly less than 3n, right? 2 is less than 3. These have the same bases, and this is true for all n's greater than 0. We know this to be true. Now we're going to use that trick, that rounding up trick, so that we can do some extra sort of proof here. So a reminder that if A is less than B and B is less than C, that's like a statement, then A will be less than C. So since we're observing that 2n is less than 3n, we're also going to prove to ourselves then that 2n plus 3n is going to be less than 3n plus 3n. And we can see that this is true. And so what is it exactly that we're going to try to do here? Well, if we can prove that 3n plus 3n is less than m times 4n, so if we can prove that this is true, and we know that this is true, it will follow that this is true. And that is what we're trying to prove. We're trying to prove that this is the inequality that holds true for all n. So since this, we don't even have to prove is true, it's just normal math. We're about to prove that this is true. This is easier to prove than this because these have the same base. So once we prove that this is true, we'll be able to conclude that this and this are true. If you're trying to equate this to the above sentence and you're having trouble, know that this is A, know that this is B, and know that this over here is the C part. And so hopefully that will help us sort of see why this roundup trick helps us so much. So the next thing we want to do is we want to shove those ends together. So that comes directly from there. And that's going to be less than 4, less than m times 4 to the n. All right, so the next thing we're going to attempt to do here is we're going to try to divide everything out here by 3n. Dividing everything out by 3n helps us remove the n's from the left-hand side of this. So we're going to do a division by 3n. That means that this and this are both going to divide by 3n. This is all positive values, so our inequality stays the same. We just end up with something that now looks like this. M 4n over 3n. Now, it's possible that this right now is looking not that helpful, but let's rewrite this statement. It can be written as follows. Times 4 over 3n, like this. And we're about to see why this is going to be helpful. So we're looking at something that looks like this, and we're going to ask ourselves, how can we actually use this information to start drawing some kind of a conclusion for ourselves? Well, having the n up here isn't that helpful when we're trying to figure out what value of n this is going to be true for. We have to find a way to bring it down. And there is a very handy way to bring it down. We can use the log rule that allows us to add the two together, which means we get something that looks like this. 4 over 3m plus 4 over 3 times 4 over 3n. Something like that. And now we have one more log rule that we can use. We can use the log rule over here when our base and our value that we're logging are the same. This exponent gets to come all the way down, and it becomes the answer to that log. So we're able to actually rewrite this as log 4 over 3, 2 is less than log 4 over 3m plus n. Fantastic. What can we do next? Well, we're trying to isolate n, so let's move that other term, this term here, over to the other side. We end up with log 4/3, like this, plus log, oh, not plus, sorry about that, minus log 4/3 of m is going to be less than n. What happens when we subtract logs? What does that actually mean for us? The funny joke is that you get fewer logs. But really what you get is division. So we can simplify this expression by writing it like this. 2 over m is less than n. All right, we have now found our n value that we need in order to make this statement true. And a reminder, if we can prove that this statement is true, and we know that this statement is true, then it follows that this statement will be true. So let's go ahead, make our way down to the bottom, and start our official formal proof. So let's start by saying let n equal log base 4/3 2 over m. And a reminder that we found that n needed to be greater than that. So we just need to add a 1. Right there, we can add the 1 to the outside. And now, given that we've added that 1 to the outside, we can observe that n is definitely greater than this statement here, right? Because n is this plus 1. So that's definitely true. We can see that n is greater than that, that log function. So what can we do now? We can effectively, we can put everything to the 4/3 base. So we're going to do that on both sides. We're going to raise everything up. We're going to put a 4/3 on each side. My unofficial notes I wrote were like 4/3 base them, because that's literally what I want to do. I want to do this. And then that's going to be greater than. Same thing on the other side. And again, if you remember your log rules and what actually this means, well, we have the same base as the log up here. When that log is up there, effectively what ends up happening is that they will not cancel out, but effectively the log up, oops, the log, wow, I'm just going to click a bunch of random buttons here. The log up here, having the same base as this, allows us to, just as we did before, we can pull this down. So what do we actually end up with is 4/3 n greater than 2 over m. So the next thing we're going to try to do here is we're going to distribute that exponent, because this exponent over here on the right-hand side, in order to actually see what we're trying to work toward, it will help if we have that exponent redistributed. So this is the same as saying 4 over n, 3 over n greater than 2 over m. And basically what we're doing here is we're just very slowly rolling back what we had before, right? So we just ran ourselves through this. We just did this. We're redistributing that base as we had before. And we're just rolling back the changes that we made before. So now that we've redistributed the exponent appropriately, we're just going to multiply both sides by n, since before we, or sorry, by n, by 3 to the n, because before we divided both sides by 3 to the n. So multiply by 3 to the n. So we end up with this. 4 to the n, 3 to the n, greater than 3 to the n, 2 over m. And we're going to go ahead, we're going to simplify what that says right there to make our life a little bit easier as well. So those 4 to the n is going to be strictly greater than 2 over m 3 times 3 to the n. Now, a reminder what we're trying to work toward. I'm just going to scroll back up for a moment. We are trying to get that that original sort of inequality that we started with when we did our scrap work, which was 3n plus 3n is strictly less than m times 4n. And as long as we can prove that this is true, we're going to be able to say that this is true just by default. So what I see happening is we're getting pretty close to that, but we need to get the m on this side. We don't want that division there. So let's go ahead and multiply both sides by m. We'll end up with m times 4 to the n, 2 times 3 to the n. And a reminder what this actually looks like. It's this. We can observe that 3 to the n plus 3 to the n is strictly greater than 2 to the n, 2 to the n plus 3 to the n. Therefore, it follows that 2 to the n plus 3 to the n is strictly less than m times 4 to the n. And we have now proven what we meant to prove given our initial n value being log base 4/3 times 2 over m plus 1. Okay, so we have now managed to prove what we set out to prove. So we can see here what's the official proof, what was our scrap work that helped us actually find that. And again, just so that we can run through this, what we'll see is once we found that value and had to be strictly greater than that, we were able to start our proof at strictly greater than that, right? With that plus 1. And by that same sort of rounding up trick, because we knew we wanted our answer to be in an inequality type form, we wanted to observe that that n was strictly greater than the original one that we found over here. We want to get back to that inequality form, and here we have an equal sign. So that's why we do that observation. After we do that, we start to move that 4/3 all the way back through, just as we did through here. So we get that 4/3 back in there, and we're able to get rid of that log after we've done the 4/3 on each side, which brings us to right here. Once we've done that, we're going to go back up and continue to look through what we did. We divided both sides by 3 to the n. So we went and we multiplied both sides by 3 to the n. What else did we do here? One step before that, let's see. Where did we? Oh, yes. And then one step before that, sorry, we were right here. We want to get back into the same form, which is 2 times 3 to the n less than m times 4 to the n. So after we've multiplied 3n in to get back to that previous form. We already have that 4 to the n. We already have that 2, 3 to the n. The only thing that's missing is getting that m back to the other side, multiply m back. After doing so, we do get this position. A reminder that at the very first thing that we did was we showed that 3 to the n plus 3 to the n is same as 2 times 3 to the n, and we did this inequality. Scroll back down, we'll see that we did that again here. We show that that's the case, and then we are able to say our final proof. Awesome. Hopefully that helps clear up this exercise for people. And as usual, if there are any questions, never hesitate to reach out. Thanks all.